Hi, I'm Aniket Patankar. I'm a PhD candidate in the Department of Mechanical Engineering at MIT. And today I'll be talking about our research on a reactor train system for efficient thermochemical fuel production. The motivation for green fuels is that as we move towards a decarbonized future, not everything can be electrified efficiently. For example, there are sectors of the economy like high temperature industrial heating, which require a steady supply of heat at more than 1000 degrees C, like steel and cement plants. There's long distance transportation like aircraft, shipping, and trucking. And at these long distances, batteries become too heavy to carry around with the vehicle. Also, we have an existing fleet of aircraft and ships which rely on fuels to run. So it would be good if we can have drop-in alternatives of green fuels for them. There's also long-term energy storage, which is over several weeks, or seasonal energy storage, where a high capex solution like batteries are not very feasible. On the other hand, storing it in the form of hydrogen makes much more economic sense. So hydrogen is really a linchpin green fuel because it can be converted into other energy carriers like ammonia, methane, and even liquid hydrocarbons like diesel using well-known processes like Fischer-Tropsch. The problem, though, is that green hydrogen is too costly to produce. The US Department of Energy recently launched a hydrogen shot, which aims to reduce the cost of producing green hydrogen from the current $5 per kg to $1 per kg. So hydrogen has been seen as the fuel of the future for several decades now. So what's different this time that gives us reason for optimism? So it's very likely the low cost of renewables like solar and wind. So the cheap renewables can translate into cheap hydrogen, but we argue that it requires some amount of storage because these renewables are intermittent. So here I'm showing different renewable technologies, their capacity factors and their levelized cost of electricity, LCOE. So the first observation is that the LCOE is quite low in cents per kilowatt hour. And the second is that there is a trade-off between capacity factor and LCOE. So solar PV has a capacity factor of only about 30%. So this is not the amount of time the sun shines on an average, but rather how much average power we can get from a solar panel compared to its peak power. So as the capacity factor increases, the LCOE, or the levelized cost of electricity, also increases. So if you're using electricity to do electrolysis and produce hydrogen, going to solar PV will give us the cheapest electricity, but the low capacity factor will cause a much larger electrolyzer system to be used and make it more expensive. So if we directly couple solar PV to electrolysis, they both will have the same capacity factor. And obviously the capex, or the size of the electrolyzer system we need, it goes inversely as the capacity factor. So with this LCOE capacity factor trade-off, the cost of producing hydrogen will very likely remain about $2 per kilogram, even with the technology and manufacturing improvements expected by 2035. And this was from a DOE study for PEM electrolysis. So there is a need for alternative technologies which can meet that $1 per kilogram price target by 2030. There is an alternative technology called solar thermochemical hydrogen production. So this includes heat to hydrogen rather than electricity to hydrogen. So we take in either concentrated solar heat or solar and wind electricity, and this can be stored at low cost in a thermal energy storage. The key here is that thermal energy storage is up to 10 times cheaper than batteries. So it can serve as an economic buffer between the intermittent renewables and the reactor system, where we'll be converting that renewable energy into hydrogen. So our thermochemical water splitting system can then operate 24/7 using this thermal energy storage. Here I'm showing a schematic for the solar thermochemical hydrogen production. We use cerium oxide as a catalyst, which stays within the cycle. There's a high temperature thermal reduction step where at around 1500 degrees C and reduced oxygen partial pressure, We drive the reduction of ceria by creating vacancies in its lattice structure to give up some of its oxygen. And then this reduced ceria 2 minus delta is brought to a lower temperature, 800 degrees C, where we can pass steam over it, and the steam oxidizes the ceria to CEO2 and produces hydrogen as byproduct. We can also use carbon dioxide as an oxidizing agent, in which case we produce carbon monoxide. And this is also a way to produce syngas with tunable composition, the H2 to CO ratio. So this can also be a means for CO2 reuse. So this technology has been around for a while, since the 1977 paper by Nakamura. But we see that the state-of-the-art systems for thermochemical hydrogen production only have a 7% heat to hydrogen efficiency. So this is the state-of-the-art system which they demonstrated in Europe in 2020. It consisted of a heliostat field that concentrated solar heat to a receiver reactor sitting on top of a tower. So the ceria was kept up here in the reactor, and it went through this thermochemical cycle, which we spoke about a couple of slides back. Some of the reasons for this low heat to hydrogen efficiency is firstly the lack of heat recovery. So as the ceria cools down from 1500 to 800 degrees C, the heat is lost to the atmosphere. And there is additional heat requirement to heat up the ceria and the reactor from 800 to 1500 degrees C. So 60% of the net energy input to the reactor just goes up in this sensible energy increase that is subsequently lost in the cool down step. So some solutions have been proposed which include internal heat recovery. So we use the heat from ceria as it cools down and transfer it to the ceria that is heating up. And that way we can gain some of the efficiency losses. The second major source of efficiency loss is oxygen removal. So this low pressure is required to drive the reduction of ceria as seen here. And vacuum pumping or other solutions to have this low pressure oxygen pumping are quite energy intensive. So that also represents a significant source of inefficiency. The third factor, which is not really a cause of inefficiency, but operational difficulties here, which is that the solar collection and the reactor are closely coupled. We use a receiver reactor, and that makes it difficult to use multi-hour storage, which we argued was one of the good things about the thermochemical system, that we can store heat at low cost. So it's difficult to incorporate multi-hour storage in these directly radiated systems. There are solutions like refractory fire bricks, which can store heat at high temperatures for several hours, but it's difficult to couple that with a reactor receiver like this. So although these individual pieces have their own solutions, what is missing is a reactor system that offers an integrated solution for all of these issues. We recently proposed such a system, which we call the reactor train system. And our analysis shows that it is 5 times more efficient than the current state of the art, which we saw in the previous slide. So the system consists of multiple carts, or these individual reactors that are carts in the train. And these reactors move around as shown in this animation. And when the reactors are in the left end of this region, we have the high temperature heat source, which radiatively heats up the reactors to drive the ceria reduction and release oxygen. And then the hot reactors are carried down to the right end, where we have a heat sink, a radiative heat sink that maintains it at 800 degrees C, where we can do the water splitting step. And then the oxidized reactors are again transported to the left to complete the cycle. What is interesting is in the middle, we have a heat recovery zone, where the hot reactors on the top can radiatively heat up the cold reactors on the bottom. So this forms a counterflow radiative heat exchanger for internal heat recovery. At the low temperature end, along with hydrogen, we produce a lot of exothermic heat. And this heat can be captured by the heat sink and sent to a power cycle, for example, to produce electricity for other systems like oxygen removal. On the high temperature end, the system is easy to integrate with the thermal energy storage, because it's not directly coupled with either concentrated solar heat, and it offers enough flexibility that we can also use renewable electricity in this system. And this provides a 24-hour steady supply of heat to the reactor train, even though the input energy might be intermittent. This shows more details of a single reactor. We have the Ceria housed shaped as a cavity for better radiative heat transfer. There's a window for sealing the reactor as well as facilitating heat transfer, and the window can be of an infrared transparent material like sapphire. Each reactor has its own insulation, and the insulation ensures that the outer reactor surface is at a low temperature throughout the cycle. So that enables ease of conveying of the reactor. And there are gas ports each reactor has for mass transfer. So with a reactor train of about 60 reactors with 1 meter dimension, our calculations show that this can produce about 100 kilograms of hydrogen per day. So although it's a huge system, it also has a proportional hydrogen productivity. These are some of the results from our analysis, which have been presented before in 1 and 2. These are the temperature profiles within the reactor trains. So the red circles are the hot reactors in the heat recovery zone, and the blue crosses are the cold reactors. And we see a nice counterflow heat exchanger profile between them. And we get more than 80% heat recovery effectiveness with this design. These are the energy flows. So the heat source or the emitter, the heat supplied by the thermal energy storage is about 500 kilowatt at an average. And we can calculate a heat to fuel conversion efficiency, which is the high heating value of hydrogen produced divided by the heat input, which comes out to about 31%, which is several times that of the 7%, which is the current state of the art. We also recover a lot of heat. This is the heat recovered in the radiative heat recovery zone. And in fact, this is higher than the heat source, the energy supplied by the heat source. We also have about 350 kilowatt of energy that's harvested in the heat sink. And this waste heat can be converted into electricity and used for oxygen pumping. Here are some more details about the mass transfer system, where we use a retractable connectors to communicate with the gas ports on the reactor. And again, we emphasize that the temperature outside of the reactor is quite low. So these are the temperature profiles within the insulation thickness. It's about 20 centimeter thick insulation. And because the thermal diffusivity within the insulation is quite low, the high temperature cycles are only felt by the top layer of the insulation, whereas the outer surface remains at a fairly low temperature throughout the system. So all the moving contacts, including the mass transfer ports, are in this low temperature outer surface. So the second challenge with the reactor train system or thermochemical cycles in general was the oxygen removal energy penalty. So this is the Ceria cycle, where we would like to remove oxygen at a fairly low pressure. And we have some waste heat at the oxidation zone to drive these oxygen removal process. The previous results, the 31% value came from vacuum pumps. But vacuum pumps have a very low efficiency, less than 5% second law efficiency at low pressures of 10 pascals. And low pressure oxygen flow has a very high volumetric flow rate because of the ideal gas law. So the pumps required are large and very capex intensive. An alternative is thermochemical oxygen pumping, where we use a second redox cycle to pump the oxygen. So this is very similar to the Ceria cycle. We use strontium iron oxide SFO as the catalyst here. And here there's a high temperature reduction of Ceria, and the oxygen absorbed by a low temperature oxidation of the SFO. So the oxidation step is on top here, and the reduction step is on the bottom. And the reduction is again thermally driven, but at a much lower temperature than the 1500 degrees C. So this effectively operates like a pump. It takes in oxygen at a very low pressure, and it releases oxygen at a 1 bar ambient pressure that we want. The good thing about this is that it's purely heat driven. It doesn't require electricity. So you can use the heat from the oxidation zone and use it directly for the regeneration or the reduction of SFO step. So this cycle has been studied previously, and many of these pumping materials are also used in thermochemical energy storage. So they are relatively well studied. The trick here was again, how do we integrate this into a reactor system? So this is our idea of integrating thermochemical oxygen pumping with the reactor train system. So we use moving SFO reactors similar to the Syria reactors. So we have an inner train of SFO reactors and an outer train of Syria reactors and an outer train of SFO reactors. And the key is, because these are mobile reactors, we can move them in opposite directions. So here the Syria moves clockwise and it releases oxygen to the SFO reactors. And in the next step, the SFO reactors move counterclockwise one step, where they get regenerated here. The oxygen is removed at 1 bar, and then the SFO reactors are sent back. And the good thing with this is that we can reach very low oxygen partial pressures, less than 1 Pascal, with the thermodynamic study that we did. And this enables us to reach very high heat to hydrogen efficiencies, more than 40%. So this is just recapping the developments enabled by the reactor train system. We can go from the 7% efficiency of current systems to 32% with the heat recovery, and to up to 41% by incorporating thermochemical oxygen pumping. The system is very scalable. For example, this is a scheme where we can use a centralized thermal energy storage and link it up to multiple reactor trains. And this single unit can produce about 1 ton of hydrogen every day, and many such units can be installed in a facility. There is continuing attention towards better redox materials than Syria, that have more efficiency and are also cheaper and more abundant than Syria. While the 41% efficiency we report is impressive, electrolyzers operate at a much higher efficiency, but that is electricity to fuel. So again, here the thermochemical energy storage can really brighten up the economics, because the thermal energy storage can be charged up within a few hours of the day, 2 to 4 hours, when electricity prices are low. So in a solar PV dominated region, between 11 a.m. to 3 p.m. would be a time when electricity prices are very low, and the test can be charged up exclusively in that low electricity price time. And we also benefit from the high capacity factor enabled by the thermal energy storage. So with that, I would like to acknowledge my funding sources, and thank you all for your attention.